And what I'll do for the actual exam slots is send around some poll to pick slots once the official registrations are in and we know exactly who wants to take an exam. I know how many slots to reserve. But kind of in this case, because there's some time that's blocked, it's worth thinking about it ahead of time. So far, so good? Or questions about that at this point? Also plenty of time. We can still discuss at a later date. We might also have to move our very last exercise class at least to a different room, because it's at the same time as our seminar on space-efficient computation. But okay, I'll let you know. What's that? It's a while to go, so everyone will forget until then. Okay, back to algorithms. If you remember, we were zooming back out all the way. We were talking about the read alignment problem, read mapping problem. You have small reads of some sample DNA, snippets of a few hundred base pairs, and you're trying to find them in some reference genome or some collection of genomes. We're building an index over those genomes to do this read mapping very fast. That's where we started, and we spent some time discussing suffix trees and all the other fancy string applications or string algorithms they allow, only to then say, yeah, suffix trees are kind of not so great in the end if you want to really implement this, because they have a large overhead in space. So we were instead looking at suffix arrays. Okay, I'm not going to scroll over this example again. Suffix array is just the starting positions of the suffixes of the string sorted in lexicographic order, sorting in lexicographic order of the suffixes, which means we're reducing the problem to just sorting a bunch of strings. That's what we discussed last time, that you can do some quicksort variant, and oftentimes this works fine. There's annoying cases where the individual comparisons between strings may take a long time because they share a long common prefix. And the algorithms are already smart enough to exploit that, and yet, because there's so much shared between all those suffixes, a general purpose string sorting algorithm has to discover this and has to spend quadratic time on such an input. And I promised we can do better, a lot better. Worst case linear time for whatever string you have. And what I'm going to show you even works for arbitrary alphabet, even if the alphabet is really big, as long as you can linearly sort it. So it's a technical assumption, if you like, that the alphabet can be sorted in linear time. Usually we think of the alphabet as being just integers, and then this is certainly true. Okie doke. In the next section, I'll show you this promised algorithm for sorting the suffixes of a string in total linear time. It'll take us a little bit to get there because it's a very clever algorithm that has a few tiny steps to get through. Each individual step, I think, is fairly fundamental or elementary, but the way they work together is beautiful. So it's spread out over a few sections. To start, we need one extra notation or one extra object that we haven't used yet, which is the inverse suffix array. Remember, the suffix array I denoted by L for leaf, because it's the leaves of the suffix tree in left to right order if you order the edges at every node in alphabetic order. And then the opposite of the leaf array is the rank array. But you can also remember it by going left and going right. That's what this picture is supposed to help you just remember the syntax. This is not so standard. People usually call the suffix array SA, and then the inverse suffix array SA exponent -1 or something of that sort. I could never remember which one was which. I found it very annoying. So instead, I'm using L for leaf array because I can remember that the leaves in a suffix tree have the starting index as the value. And the suffix array as well has the starting index of the suffixes as the value. And the position is the lexicographic order. The inverse is the rank of a certain string. If you have a starting position as an index, then the rank array tells you how many other suffixes are smaller in lexicographic order. There's many different ways to say the same thing, and they're written down here. You can define it as the inverse permutation by having the index and the value flipped as it's shown here, or it's the number of the rank array has number of suffixes smaller, base 0. The other option to remember this, which I find visually most sticky, so I'm going to spend a minute explaining it. It's natural that you start with the text and just write down all the suffixes. That's my postulation. And so you write them down in the text order by starting index. Then you get this nice triangle shape. And on the right, you have the same strings, but now in sorted order, lexicographic. And then here, what you have is going down the rank in sorted order. And what you don't know is the index. That's the leaf array. And on the right, on the left, you have the rank array. Now, this going left and going right means if you have an index here, you know where the string starts, and you'd like to know where it is in the sorted order. You take the R array, you want to go right, and it tells you, this is at index 6 in the sorted order. And vice versa, if you have a string where you know it's the penultimate in the sorted order, index 8 or rank 8, the leave array tells you where this guy starts. Okay, going left. Maybe it helps you to memorize this. If not, you just have to scroll back. So with that, let's tackle the actual algorithm to compute the sorted suffixes. And it turns out it's more convenient to compute the rank array and not the leaf array directly, or the suffix array. But as this picture, hopefully, and this definition shows, if you have one, you can compute the other in linear time by just going through a loop and setting, going through a loop of I and setting I at the position of R. Right? It's the inverse permutation. So we can compute either of the two, whatever is more convenient. And here we'll compute the rank array. The algorithm, now there's several algorithms. I'm presenting just one. It's called DC3, or the skew algorithm. DC stands for difference cover, and the 3 means there's other alternatives. You can forget about that. I just wanted to mention why there's this weird name. And it does an awkward thing. It first recursively computes some of the ranks, namely for all of the starting positions in the text that are not at a multiple of 3. So for 2/3 of the input, you compute recursively what the solution should be. And then you use what you've computed to infer for the other third, the sorted order, or the rank array to be specific. And finally, you merge those two to get the sorted order for the overall list of suffixes. We'll keep moving between these two worlds, having indices of a certain type and thinking of them as the strings that we sort. So this merging step, you should think of just the rank arrays give you the sorted orders of these suffixes. So of course you can merge them in essentially the standard way. Whereas for this second step, we exploit a bit more crucially that we're talking about suffixes. And for the cost for the merge, we'll have to look at this carefully as well. Before we look further into how to do all this, let's try to analyze the results. And here I'm just going to forward reference that steps 2 and 3 will take linear time each. And then standard Master's theorem, if you have total cost linear in the first step, then recurse on 2/3 is a geometric series. So the total cost is also linear, because you get rid of a constant fraction of the input in each step. So if we can do all that, we're good. Then we have a linear time algorithm to compute the rank array, and from that we can compute the leaf array, the suffix array. Let's look at the second step first. We'll come back to the first step. Conceptually, it's just recursion, so that's easy, right? Where we have to do the actual work is in the conquer step. And the second step says we've recursively computed the sorted order of all those suffixes that start at indices that are not a multiple of 3. So the 1, 2 stands for the remainder by division of 3 of the starting index. That's these guys. And knowing their ranks, we want to sort the suffixes that do start at a multiple of 3. How could we do that? And in linear time, please. Well, for that, we clearly have to compare these suffixes that start at, say, position 0 and 3, all the multiples of 3. We could do that character-wise, but that might be too expensive if they share a lot of common characters. Also, we still need to kind of sort, so just using a black box sorting algorithm wouldn't work either. But they're strings, and you can compare them. So if you start doing that, you compare the first character. There's two cases. Either the first character already decides who is smaller, or it doesn't, in which case it has to be equal. Then you have to look at the following characters. But the following characters after T0, the suffix that starts at the beginning, that's the suffix starting at 1. And same for T3, if you remove the first character, you add T4, the suffix starting at position 4. And for those two, these are both in R12. So for those two guys, you already know the rank or how they compare. You can look up the rank and compare the ranks instead of the actual strings. So instead of comparing potentially many characters, you compare a single integer. Also, we recursively computed this, and its suffix is terminated by $, so there can't be ties. There will always be a definite outcome, strictly less, strictly greater. These two together we can combine into a single check by saying we're comparing pairs of a character and an integer. The first is one character of the string, and the second is one rank. And we compare these pairs in lexicographic order. And that's the same as comparing these suffixes. Okay? Now, this is actually easy to do. Let me show you in an example what this looks. But already at this level, we're sorting pairs where both components are of a small and fixed size and integers. Let's say the characters are integers as well. So of course we can use counting sort or radix sort for that. As a concrete example, just because it prepared it anyways, here's the long text. Here are the recursive call sorts all the suffixes that start at not a multiple of 3. And technically what it gives you is this rank array that tells you for every starting position the number of suffixes that are smaller. I wrote them down here in sorted order, but of course, I guess you can imagine what this looks like. And here are the suffixes that have a multiple of 3 as the starting index, which we want to sort now. So we take their first character and then replace all the rest with the rank of what's left, which in each case is just the suffix starting one character later. And that's always 1 where we have computed the rank already. Okay? So instead of dealing with this to sort, we're dealing with this to sort. And with 2 rounds of counting sort, we can do this in linear time. Linear in the number of guys here, which is certainly O of n in total. And that's our rank array for all the suffixes that start at a position modulo 3 equals 0. That's step 2, which created from this 2/3 list, the 1/3 list. Next, we have to merge. We're given the 2 sorted inputs as runs, and try to produce the merged result. And as you may imagine, we can try to do a similar trick as we did now. We look at maybe a few characters at the beginning and hope that the rest can be settled by doing an integer comparison. What we're doing is essentially the standard merge method, which already is linear time if every comparison takes constant time. And we have to use what we've pre-computed to speed up these comparisons. But let's just start in the example and see what happens. Suppose we've already merged a few of these suffixes. Now that means we're sitting here and here, right? So the question now is T15 or T11 smaller? And of course you could look at it and just take the string, but let's pretend we're an algorithm and can't. So here are the two suffixes. We split off the first character and are left with some slightly shorter suffix in both cases. But if we do that here, we turn the green suffix, one from the guys here with multiple of 3 index, into a blue one, and vice versa. So we can't directly compare their ranks, because I guess this is maybe a subtlety I didn't point out. The ranks here in R12 and in R0, these are local relative to this collection of the data. They go from 0 to 14 here and from 0 to 7 here. So if you take numbers, one from here and one from here, they have no meaning, right? So that doesn't work. And so it seems that trick fails. But luckily, if you just go on one more step, it works. By splitting off a second character, you always end up with 2 blue guys. Now you could analyze a bit more clearly, a bit more generally what you need for this to happen, and that's exactly where the difference covers come in. You need some structure of separating the starting indices so that when you split off a constant number of characters at the beginning, you always end up with something that's in the same set. One option is the chosen, and I'll leave it with that. But that's one way to generalize the algorithm. So again, the trick is you're trying to compare something where you don't exactly know, and you can't use the rank arrays directly. But if you split off either 1 or 2 characters, and this depends on what the starting index is, you're guaranteed to find 2 blue suffixes for which you do have the ranks, and then it stops. So in this case, you need 2, but that's already the worst case. In either case, the comparison you need in every step of the merge can be decided in constant time after checking 1 or 2 characters and 1 rank. Well, at most that. So you can also do merge in linear time, and that means we've completed step 2 and step 3 in linear time. So all good. Now what's left to say is that, oops, we cheated a bit, at least conceptually. There's different ways to solve this, but I think the narrative here makes this very clear. If you remember what the algorithm said, it said recursively sort the suffixes that start at these indices not a multiple of 3, R12. But what does that mean? Recurse on what? Like, we can't just take a subset of strings and pretend that that's the same problem. It's not, right? So we somehow have to make it the same problem if you want to stay close to the original formulation. And indeed, that is possible. You can make it work by constructing a specific string t prime that's constructed from t, so that you can recurse on that string and you magically compute the right number, or the right answer. So we want a string t prime that lets us skip certain indices in the starting positions for suffixes. Well, to do that, we just bunch characters together and treat them as a single character. And in this case, what you have to do, because you're essentially doing everything modulo 3, is consider triples of characters. So instead of this input string, t box, the tripled string, is just taking these first three and pretending that's one character, it's one item. And then, of course, the suffixes of t box are precisely, ignoring the box boundaries, then are precisely the suffixes that start at multiples of 3. Now, this is not exactly what we wanted, right? We wanted the ones that don't start at multiples of 3, but you can tweak this idea a bit. You take the ones that start at a multiple of 3 plus 1 and a multiple of 3 plus 2, so you concatenate 2 of these strings. And that's our t prime. Then the suffixes of this guy, if you ignore the boxes, are precisely the suffixes of the original text, where the modulo 3 is 1 or 2. So we can construct this string and then recursively can sort the suffixes of this string, which, because we only return a rank array, only the integers that tell us how many other suffixes are smaller, we don't even need to know that we've changed the string, right? It works the same way. Good, so that's that fixed. But now we created a new problem because we cubed the size of the alphabet in each recursive call. And that you can only do for a few times before it gets so big that you can no longer use counting sort. At least in the simple way, right? What we did to sort, at least in step 2, for the induced sorting step, we needed that we can do a round of counting sort on individual characters. In the recursive call, these get bigger and bigger, so we need space proportional to the size of the alphabet. That's going to blow up. Okay, so we need to fix that as well. But luckily, this is only a fake problem, if you want. Because from these triple characters, there might be sigma cubed different triple characters in existence, but we cannot have more different ones in our actual string than our string is long. So no matter how big the alphabet, our t prime will only contain at most 2/3 n different such characters. So we can just give them new names. As long as these names preserve the lexicographic order, that's fine. Again, all we return is the ranks of the suffixes, nothing with the strings specifically, so we can rename the alphabet and nobody notices the difference. So we do that, and what we do for that is again sorting. We sort the triples. That's again counting sort 3 rounds and replace every character, the triple of 3 characters, by a number which is the rank of that character among all the occurring characters, among all the occurring triples. And that means sigma remains less than n in every step, and then we do get the same behavior in the recursive calls. And so, pinky promise, that's it. There's no more nasty surprises coming up. Here's an example for how to construct this string t prime. That's the text from before. You construct the text where you leave the first 2 characters off, and here you leave the first character off, and then break it into blocks. To make it work nicely, you have to include the right number of $signs, but this is it's not a big deal. Then in this small example, there's almost all occurring triples are unique. There's just this one here, Anna, that's repeated. But fine, so here are the triples in sorted order, and then you can replace every triple by its rank. Okay. So again, that was the overall algorithm. We spent some time figuring out how to do the second and third step in linear time. And we found even the first step can actually be implemented, and it's not causing more trouble, but it does cause a bit more effort than it may first look like, where you just say, I just do it recursively. You do have to construct this, this t prime and do the renaming of triple characters. Now, if you wanted to use this in practice, there's good libraries available that do suffix sorting. So it's rarely so necessary to implement from scratch. I want to show a few details of the original paper for this algorithm, how they implemented it, just because it's a few cute tricks. These might no longer be the most efficient practical solutions, but I think the description from here, there's still a certain gap from there to go to a clever implementation. And so I'll focus on some of the nice steps and show them in the most simple possible way. It's not the fastest possible way. The key component that their implementation builds on is a clever implementation of counting sort or radix sort. One round of radix sort is what they call it. I think we would say counting sort. It's clear that we need this conceptually because we're doing several rounds of counting sort with specific either characters or then integers later. What they figured out is what you really want is sorting some indices. So you're only picking this array A gives you indices in this array V, and you're sorting the indices according to what value they have in V, which allows you to conveniently specify sorting certain subsequences by just giving the right indices, and you don't have to copy out the data. You just copy out indices. K is what was sigma before. That's the range for the values. And we return again an array of the same indices in A. So you're sorting the indices in A with respect to the values V. Maybe it sounds more complicated than it is. So first step is counting sort. You count how often each value occurs. That's this part. You take the value of the ith index and increment that counter. Then you do prefix sums of these counters. Then you turn the count, by that you turn the counts into the target indices for the sorted order. So this just computes the cumulative sums of the counts. And then for the sorting, we create a new array as output where we put the indices in. And we go through the range of values of indices, pick the first, and write as many copies of that into. So we go through the unsorted input and write that value at the right position. What we really write is the index of that value into the position in B. And for that, we use the count array to know where to write to, and we increment that counter to remember that we've already used up one space. So you could think of the count array here as simultaneously moving through portions of the index space, and you don't know in which order you increment them because that's given by the input order, but at the end they will all have scanned over their range for the value V. Okay, that's the specific building block they use. And particularly the first step, I think they solved really cleverly. That's the final algorithm if you want. You're given a text, you're outputting the rank array. You compute the sizes of the three parts, which if you include the proper rounding are a bit annoying, but by and large they're equally long n over 3. Initially we start with R12. This will eventually be the rank array, but you first initialize it with the indices that are in R12. So it's all the indices that are not a multiple of 3. And now you compute, for the reduction of the alphabet, the sorted order of these triple characters. And for that we use this radix pass I just showed. we sort the integers, the indices that are in R12, but we sort them according to the last of the triple characters. That's why here t is offset by 2, so that you're using the third of the triple characters. From the result of that, because this radix sort is stable, you then go sort these guys according to the second character of the triple, and finally the first character of the triple. So after that, temp will have all the indices in here in the sorted order according to the triple that starts at that position. It's a bit convoluted, but kind of clever, right? Now we have this in sorted order. Now comes the renaming step. You go through all the triple characters and you check, is the current one the same as the previous one? If so, it gets the same name. Otherwise, you increment the name. And then this step is another stroke of genius, that you can compute the index where you should write it to from, again, the modulo 3. Now, after this, you have in R12 the new names of the triple characters that started at these positions. And now comes another clever trick. If these triple characters are already unique, there's no duplicates at all, then these determine the sorted order for the entire suffix, because they already fully determine the order. And then they coincide with the rank by pure chance or genius, because they start at 0 and go up to whatever the number is, n12, right? So then you don't even have to recurse if you're in this lucky case, and that's also the base case, the kind of both in one. If not, then you do have to do the recursive call, and then you get the result back. The merging and the induced sorting is actually not so interesting. It's similar to how we did it, so I didn't provide the code. If you want to see their lovely C implementation, which is deceptively short and has a few more tricks that I removed, then I mean, there's the paper linked. I think it's impressive at the very least. Clever piece of engineering. What you should take from it is more on the conceptual level, that we do the induced sorting and merging step by essentially relying on this asymmetry between this bigger subproblem that we recurse on and the smaller that we induce from it. That part, I think, is worth remembering. The implementation details, as I said, is maybe more for the nerd amusement. I don't know. All right, but we do know how to sort suffixes in linear time now, and there's nothing really fancy needed for it. It's all counting sorts in one way or another. Okay? Nothing very complicated else going on. Let's take an intermediate conclusion for suffix arrays. Is, as a data structure, is just an array of numbers. So that's as plain as it can go. You can have a simple, for most strings, you can do a simple string sort, and that gets the job done. But of course, you can also go full Monty and implement the linear time solution. We'll call a library. And we can do reasonably efficient string matching with this, despite having gotten rid of all the tree structure on top. But it's not quite as fast as suffix trees allow you to search. Right? At least string matching itself, you need to do a binary search in the suffix array, but also each comparison takes, worst case, m character comparisons, because you may have to compare two strings of length m. So that's a good deal worse, and we'll work on that in the next chapter a bit. But what's more is, suffix trees can do all these wonderful things for string algorithms, and that seems lost for now. Suffix arrays only give you the sorted order of the suffixes, and all the other ones. Remember the tandem repeats and all, so much fun that we had before Christmas. All that seems harder to do with just suffix arrays. Do we need a break? By the way, it's almost time. If you don't stop me, I'm not gonna take the break.
Can you show like the 36, I think?
Ooh, that's a while ago. Okay. The merging.
For this example, for the right side bottom T12,
Yeah.
I understand that purple one is because there's NA, and below it becomes AA, NA. Exactly there and below it.
Yeah, I don't think it should turn into an A.
It should be N.
Yeah, that's an N. Funny, yeah. I mean, there's a certain chance it's copy pasted from here, right? And I forgot to change it to an N. It's otherwise the right suffix. Yeah, cool. I was using this slide for many iterations. There's nobody ever read through the example, it seems. Yeah, no, you're right. Which also means in this case it's a kind of bad example because here the character would already decide the comparison, right? The S and the N, you would already know N is smaller and you're done. You don't need to check the rank of 17 and 13 even. I think I tried my best in this small example to find something where you have to go 2 steps, but the character doesn't decide it straight away. I mean, I have to have the same first 2 characters, so probably I should have picked this guy instead. Other than that, there's no... It's curious, there's no AS in this one. Well, only one AS. Or I could do these 2. Right, that might be better. You need a green suffix and a blue suffix that have the same first 2 characters, right? For the interesting example. Now, for 6 and 10, I'm getting to 7 and 11. These are both not, yeah, so this is bad from that perspective. So you see, finding good examples is actually hard. You have to... Yeah, that's better. That's right. Okay, so I have to go all the way down there. Yeah, good spot. Nice. I think it's worth updating at some point. Okay, I think that counts as the break, right? Yeah, I'm a bit afraid we might lose all of the phylogenetic tree chapter otherwise. But then again, less for you guys to prepare for the exam. It's also fine. In the next section, we'll look at this very last criticism from the previous round where I said, oh, suffix arrays, they can't do all the magic tricks that suffix trees can. And it turns out that's ultimately wrong. You can make them as powerful as suffix trees, but you have to work a little harder to get there. And the first very crucial step is what's called the LCP array, the longest common prefix array. Which gets you a good way towards supporting most of the things the suffix tree can do. And we'll build a bit more on that. Because it's a while ago, I thought I'll leave this one in. One of the early applications of suffix trees, which I guess you may guess at this point, you cannot easily do with just the suffix array, was to find these longest repeated strings. Okay, I started it now for real, and you can log in the answer if you want. That algorithm to find the longest, or say the length, to be precise, just the length of a longest repeated substring, we used some other feature of suffix trees beyond just the sorted order of suffixes. Which one might that have been? Is one of you still thinking? Shall we wait for a short bit? As this might be it, so the memories will come back, but you got it. It's for just knowing the length. All we need is really the string depth of the internal nodes, because every internal node has at least 2 leaves below it, otherwise it wouldn't be there. And so it corresponds to a string that shows up twice. And that's an if and only if you think about it. So finding any node with deepest string depth corresponds to a longest repeated substring. For that, we need these string depths. Now, the suffix arrays don't have those. Here's again how we did this in suffix trees. Just have the picture again. Suffix arrays by themselves don't have this. So we'll add something so that this information is present again. And that's the LCP array. You should think of this as visiting the leaves in left to right order. And then between any 2 adjacent ones, say these 2, as an extreme example, but fine. Between any pair of adjacent leaves, there's precisely one lowest common ancestor. There's one internal node that splits these. And that's the lowest common ancestor in the tree. If you walk up, their paths to the root will join at some point. And that node's string depth is what we're interested in. And that turns out to also be the longest common prefix of these suffixes that start at those 2 positions. Because again, think about it, what it means in the suffix tree. If you traverse with the suffix starting at 1 from the root down here, and the suffix starting at 6 from the root down here, they share a path until they don't. At that point, they split. And that must be their longest common prefix. That's the number of characters they have in common. And so the algorithm for finding the length of a longest repeated substring could be just find the maximum in the LCP array, full stop. That becomes trivial. But of course, that is once you have the LCP array, which for now we've just defined, but I haven't told you how to find it. Yeah, again, the important point is that we compare the suffixes in the sorted order. So in a way, the mnemonic should be longest common prefix. We want these to be really long, and they are maximally long if you compare strings that are close in the sorted order. They tend to share a lot. That's the order in which we write them down. And as a nitpick, the LCP array in my notation starts at 1, whereas all the other arrays start at 0, because it takes the leaf of the suffix of a certain rank and the previous one, and I can only do that starting at 1. What you really want to think about is that the LCP array sits between the leaves. It's a bit annoying. We can't write that more conveniently down with 0.5 as indices. That's what it conceptually should rather be. There's another nice connection I want to show in this picture. Here's the leaves and the suffixes that correspond to them. And here are, in the sorted order between each pair of adjacent suffixes, there's the longest common prefix written down in red. Then the LCP array is the length of that shared prefix. That's LCP by definition. Now, you can, from this array, say there's a certain range. Everyone shares the empty word as a common prefix. Some ranges, say this range, also shares the A as a common prefix. And then there's a sub-range here that also shares A and N as a common prefix, and so on. So you can draw what is shared as common prefix. And if you now add the suffix tree again, suppose we have it, then you see these ranges of shared common prefixes one-to-one correspond to internal nodes in the suffix tree. Specifically, like in this case, it's important to say if there's a longer shared prefix that has the same extent, it's shared by the same set of leaves, then you only look at the longest. There'll be a single internal node in the suffix tree for ban, not for the intermediate steps that would be unary nodes. But in a way, this already shows you, if you have the leaf array and the LCP array, you kind of have the suffix tree at your disposal, because these intervals where the LCP is above a certain threshold, that corresponds precisely to internal nodes in the suffix tree. So it's LCPs are useful way beyond the simple finding longest repeated strings. They can indeed reconstruct the suffix tree. And I want to make this more explicit and give you the actual algorithm to compute the suffix tree from these two arrays, which also is a good opportunity to close for good one of the black boxes that we left open previously, namely how to find a suffix tree in linear time. I've told you for suffix arrays how it works. I will tell you how it works for LCP arrays. Just give me a few more minutes. But once we have these two, we can construct the suffix tree from those two without much further complication. So conceptually, a suffix tree algorithm, which is, I think, more efficient than many of the previously known Dirichlet ways to compute the suffix tree, would be to find the suffix array, compute the LCP array, we'll see how to do that soon, and then from those two, compute the suffix tree. How do you do this third step? There's a cute, inefficient way to describe it recursively, so I'll show you that on the example, and then there's an efficient, maybe even cuter way to do it, but is a bit less transparent. So that's on the next slide. Here's the leaf array. That's the leaves of the suffix tree we're trying to build. We'll essentially just work on the LCP array, though. And the recursive method says there's going to be a minimum in the LCP array. Initially, that has to be 0 because it can't be negative. And there have to be some strings, or at least here I'm adding these dummy sentinels at the beginning and end of the LCP array to have zeros for good. So the minimum will be 0. And it might occur several times. Specifically, there's a 0 here, and a 0 here, and a 0 here, and the dummy 0 here. That's going to be the top level split for essentially the root. So there will be a root. I'm drawing it a bit elongated so that the labels, the edges to the children are a bit easier to see. And we'll recursively apply the same procedure to all the ranges between the red lines. But then what you get back from this is added as child to the root. Okay? And so here, still to compute, still to compute, still to compute. And this could be an individual single leaf. And of course, we'll have always this one because it's the dollar, but okay. Yeah, you may forget about this. Doesn't matter. Let's recurse on this part where we'll only look at these guys now. So the minimum here is the 1. And you can, again, pretend to have dummy ones at the outside. So I'm not going to draw the red lines another time, but kind of you always have the boundary at the left and right end, or upper and lower end. So the next division here will be between this and this part. And we'll have an internal node sitting here that has the 5 as one of its children. The other child will be recursively computed here. Let's keep recursing. So now instead of this, we're looking just at these 2 entries and these 3 leaves. Again, we're finding the occurrences, all occurrences of the minimum value. There's just the 2. So here we'll look at this range. And that means there's an internal node here that has the 7 attached to it. And well, guess what? If you're recursing on one with a single LTP entry, that can only get one more internal node connected like this. Okay. This recursive call is also trivial. This single node with these 2 attached. And here we have another simple one with 3 leaves. This one will come first. So it'll have to look like this. And that's the tree topology. So you should tilt this on the side. We'll flip it to the other side, and then you'll see it matches exactly this tree. It's the same topology, just mirrored to the right. So you flip it vertically. Now this algorithm is fine, but it's not so efficient because the trivial way to do it would be to rescan the LCP array to find the occurrences of minima. So that may not be so efficient. You can avoid this by going through the LCP array once from left to right and build the suffix tree for a prefix of the string, or that's not right, a prefix of the leaves and LCP array entries. And in each step, just add one more internal node and one more leaf. And that works in total linear time then. The technical way to do it, I was fighting a bit with the best way to write it down, and I decided to do the insertion in the edge in the end because it's still cleanest. You start with a single vertex to hold the single leftmost leaf. Then the crucial invariant is that we maintain on a stack the right spine of the tree. So if that is your current suffix tree, let's do one more here. I'm going to keep these 2 guys. That's the right spine. I'm following the rightmost child pointer down until I reach a leaf. These 2 I'll keep on a stack from bottom to top, so root downwards. Then when I get the next LCP array value, the LCP value, that tells me how deep the next node has to go in the hierarchy of the tree. It could go up here, or it could go between those 2, or it could go down here. And each case gives a slightly different tree. In this first case, we would have the new node as the new root, and essentially the rest of the tree is a left subtree. Now I regret that I drew it so big. And there's one new leaf that also comes into existence. That's for part A. That's if the new node has a smaller LCP value than all the previous ones. Another option would be it's between this and this. Then you would keep the original root. Then you would have the new node. Then you would have this left child here that still hangs here. That's not right. This guy is missing. So there's the new node here. Oop.
You have to tap the panel.
It's my reminder that time is running out, eh? So here, that's the new leaf. That's the new node. That's the same from previous. You're essentially inserting into this edge the new node. So you're pulling the edge to the right and plugging in a new node. And then the left here is unchanged. And the third option is similar. In each case, all you have to do is essentially bend away a constant number of pointers. You have this one from the parent down here, and from this, the child. That's what you have to change. And in the code, what you do is you pop from the stack the right spine until you find the spot where you're supposed to go. And then you insert your new node there. And because you're essentially pushing every node once and popping every node once, whenever you do effort, it could be that some insertion takes a longer time because you have a long spine to work up from. But then all these nodes are gone for good, and you can't have another expensive step afterwards. In a way, what you're doing with the stack is scattered over time, one traversal of the tree. So it's linear time overall. I should say the algorithm only outputs the shape of the trie and doesn't label the edges with the corresponding characters, but that's easy to fix. You can look into the text and pick the right edge labels. Easiest conceptually to do this in a second traversal. And as you may have recognized or not, who knows, this algorithm is similar to some other known algorithms. And if you want, you could say the topology of the suffix tree is the Cartesian tree of the LCP values. If that helps you, then great. If not, fine, ignore it. Like the algorithm works without that understanding. Okay. So with that, we can properly compute the suffix tree if we wanted to. But we'll try to get away from that. The last missing piece is how to compute the LCP array. We found good use for it now. Now we're eager to construct it as well. And clearly it has to be linear time. Otherwise, we're not happy. We have to do it in linear time, which means we can't naively just compute it by scanning. So one option is if you have the suffix array, you could just take your adjacent suffixes and compare them. How many characters do they have in common? And write down the number. But in an extreme case, the text of all A's again, each of these steps could essentially be linear time. So quadratic overall, no good. We need something smarter. And the key idea is best seen on an example. This procedure is expensive exactly when the numbers in the LCP array are big. But when that's the case, we actually know quite a bit. Just the knowledge is a bit inconvenient the way it presents itself. Let's look at a long text with a lot of repetition so that there's a good chance for long shared prefixes. That's this lovely text, buffalo, 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 which you can add a substantial amount of buffaloes to, and it still makes a grammatically correct sentence. But that's besides the point. Let's say you take the first suffixes of this text in sorted order. First one is just $1, but then things become a bit more interesting. There's all these guys starting with ALO. I wonder why ALO dollar is missing. That's before the space, right? Whatever, somehow that got lost. There's maybe another character that is not printable, so you don't see it, and it messes up the sorting order. Let's pretend the text has these suffixes. My point is, if you have two suffixes that are adjacent in sorted order and they share a long common prefix, guess what? If you take away the first character of both, they still share essentially the same prefix except for the first character that they both lost. So if the LCP here has a large value, removing the first character gives you another place where there's a long shared prefix. The only problem is that we don't know where that is, and it might even be nowhere at all, because who knows if chopping off one character leaves these two suffixes adjacent. Maybe there's another suffix now that smuggles in between, because we've removed a character. A lot of things could happen. So this insight is useful, but using it productively seems to require a trick. And the trick is what Kasai et al. Used for their very lovely algorithm, which is just compute the LCP values in a clever order following your knowledge, and then you can maximally reuse what you've learned. If you ever spend a lot of time following many shared characters, you can profit from that for a good while and produce many big LCP values for cheap. So how does that work? Again, my favorite picture from before, the suffixes in text order, suffixes in sorted order. Kasai et al. Says, just compute the LCP values in text order and everything will fall in place. Let's do that. The first is obviously this one, the entire text. Now, this doesn't get an LCP value. An LCP value is always between a suffix and the previous one in the alphabetic order. So for knowing which one that is, we have to move to the right. So we use the rank array and find that we're actually working in position 6 here in the LCP array. And the previous suffix is this guy. Now, initially we know nothing, so we have to pay for finding the shared prefix. And here it stops. So we can compute we can write down our first LCP value, 3. Now we want to maximally reuse what we learned, or maximally reuse the work we have done. So we get rid of the first character, which is the same as moving to the next character, next suffix in text order. But where is that guy to be found? Well, we have to look at the rank array and find it over here. Now, it has some previous suffix in the sorted order, and we don't know if that is ban without b. It actually isn't, right? That one's up here. There's someone else in between. But these two shared an, these two shared an. Everything in between has to share an as well. Maybe more, but at least these two. So we inherit that these two characters are shared. And we can start computing the next LCP value from 2 onwards. And in this case, we did get another shared character that wasn't here before. So it's another entry 3. And we keep going like this. I animated the entire example. So we go to the next suffix in text order, find where it belongs here. We inherit the 2 characters and check if there's more. There isn't here. So it's just a 2. That's it. Going to the next one in text order, find it over here using the rank array, inherit 1 character, check 1 more, another LCP value 2, and you keep going. Okay? And that way, you see, if you ever have to scan a lot through the text, that's fine, but then you're not going to pay in all the subsequent large LCP values much more because you've already made a good way through the strings. It gets shorter and shorter as you go through. And if you write this down as proper code, you get something like this. There's an outer loop for the position in the text. That's the scanning on the left. Then you find where are we on the right. you find the position, the starting position of the suffix that is one above you in sorted order. That's the I-1. And you may have remembered some shared characters L from the previous iteration, initially none. But you skip the first L characters of these two suffixes when you do the comparison. As long as they're equal, you increment L. Once you're done, L is the LCP of these two suffixes. So you write that one down, and for removing the first character, make L1 smaller, unless it's already 0. And then you repeat. I think in code, this is even simpler and maybe subtler to follow than in the example. So I hope the order of presentation helped. Let's quickly analyze this. That's clearly in the code even clearer. The dominant operation is the number of character comparisons. And as for sorting, remember from last time, even it's a while ago, it's clever to compute the number of comparisons you do separately for the ones that come out as equal and the ones that come out as not equal. The ones that come out as not equal are always those that stop this inner loop. And that means there's one of them per outer loop iteration, so linear. It's only one per value of I. The ones that come out as equal, there may be maybe many, but they always increment L. And L always remains below N and is decremented only by 1 here. So you can't increment it by more than 2n over, by n overall. I guess 2n overall, right? Yeah. You increment it once here, you decrement it once here. At most 2n for sure. So you have a linear number of character comparisons in the entire algorithm. So the entire algorithm is linear time as well. Now, because these are so useful already, this combination of the suffix array, maybe with the inverse suffix array, and the LCP array has been given an extra name, the enhanced suffix array. Maybe it's not a good name, but it is a name. It usually means at least these 3, sometimes additional structures. And you could say it's the modern version of suffix trees that when you try to solve string problems at scale, you would go to such an approach as opposed to suffix trees. It is a bit harder to reason about, at least for me personally, but anything about the implementation speaks for it. One good way to think about them is design an algorithm for suffix trees and then compile it to work on enhanced suffix arrays. Usually is actually not the second step is not hard to do. And indeed, we've seen for many of the things you can do on suffix trees already how to do it. For example, string matching, we kind of saw, except that with a slowdown, but we'll work on that. The cross here doesn't mean it's not possible. It's just that we haven't done it yet. We've looked at LCP values. The internal nodes in a suffix tree are essentially the LCP values or these intervals. So we kind of have those. What we haven't looked at is longest common extension queries. And remember from even the chapter before suffix trees, we've heavily used them for the inexact string matching. And we left it as a black box how to do them. So that's up for next time. And there's another nitpick on suffix links, essentially the things that showed up in AHO Corosic that you could add easily to suffix trees. And we haven't talked about it for suffix arrays, but these are easy. The main open one is this one and the matching time. Okay, that's all for the suffix trees that we're done with. There's a little bit time left to start with the next part. Well, we'll try to work a bit further to the actual solutions for the read mapping problem. We can, by and large, pretend that that's string matching, either because we say it's good enough to have exact matches, we're doing a simpler version, or because we say, we're using this reduction for, say, these SNPs, the single nucleotide polymorphisms. You can kind of solve, you can do exact matches and then use the seeding algorithm. All the inexact matching algorithms build on top of this. So let's first get this part sorted. So that's what we'll look at next. And I'm also hoping to give some ideas of how to reduce the space of the entire structure even further. Already we said suffix trees take a lot of space, suffix array is better, LCP array and suffix array together are still better, but we can do even better. In this next unit, we'll move closer to the state of the art for string indexes for large texts, in particular bioinformatics genomes. And that will build on the suffix trees, but extend them a bit. To make better use of our LCP array that we've introduced in the previous unit, we'll talk about some useful black box that, first of all, may not appear to be directly connected, but is precisely what we need for making better use of LCP arrays. And then we'll see some applications of this and at least the ideas of how to reduce the space further in modern indexes. We've also left open this business of computing longest common extensions. And that's been burning under my nails to close. So maybe the same is true for you. Remember what this was. We had a string and LCE queries are given to positions in that text. How many characters do they share? Already at the time, we connected it to the suffix tree in the following sense that the longest common extension of two positions in a text is the longest common prefix of two suffixes. So the LCP array seems to be getting towards the answer. But the LCP array only has entries for two adjacent leaves or two adjacent suffixes in sorted order. Whereas here the LCE queries need arbitrary suffixes as input. You can still use the suffix tree in this way that longest common extension of these two, if they're not adjacent, is still given by the string depth of their lowest common ancestor in the tree. But that means we have to know how to compute lowest common ancestors in a tree, which we also haven't covered. So either way, we're kind of running in circles here. But we're connecting things, making connections between knowledge is probably still useful. And I promised at the time that we can somehow do this, formulated here for the lowest common ancestors in trees. But as you see, it's equivalent to here talking about the longest common prefixes of arbitrary suffixes. The promise was we can do this in linear time, linear space, and then for the pre-processing, and then constant time per query for longest common extensions, or LCAs. To get there, let's look at a different problem. And you'll see soon how it connects. But let me first define it. The range minimum query problem is the following innocent task. You're given an array of numbers. And you can look at this array of numbers in a pre-processing step. And then there's a query phase, same as for longest common extensions. Now I'm asking you queries, a range from I to j. Where in that range is the smallest value in the array? This sounds cute and useless. Why would you want to answer these queries? But bear with me for a bit. Two nitpicks will insist on reporting the index of the minimum, not its value. Because we have the array at query time, we can look up the value if we want it. That's just a bit more general. And if there's ties, we insist on getting the leftmost position of the minimum. That's just to make it well defined. Neither of these is really critical at this point, but keep that in mind. That's our definition. So as an example, in this array, if you look at just the red range, the minimum value is 2, and the leftmost occurrence of 2 is at position 10, so 10 is the answer. What does that have to do with longest common extensions, longest common prefixes, and lowest common ancestors? Well, everything. To compute the longest common extension of 2 positions in the text, in other words, the string depth of the lowest common ancestor of their in the suffix tree of these 2 leaves, or the longest common prefix of these 2 suffixes that start at position I and j, you just take the smallest value in the LCP array there. Here we really need the value, not the index. That's why the result of this RMQ query is put into the LCP array. So we really read the minimum value. So all this says is you're finding a range in the LCP array and give me the minimum value. And now I'm going to do this dangerous thing of trying to zoom in a bit. It's slow. I don't dare to do it faster. It's been crashing a few times in other cases. Why is this correct? Suppose we want the longest common prefix of these 2 leaves, or in other words, the suffixes starting at position 5 are A-ban and 1 are a nanoban. What's the longest common prefix of those? Well, you can look it up from the strings. It's just the single A. But you can also take the 2 and look at the corresponding range in the LCP array. And if you think about it here in these LCP intervals, clearly the lowest dip that you have between these 2 endpoints is going to dominate the answer. If there's a shared common prefix between all these strings from here to here, it has to be one of those intervals, or within one of those intervals. The lowest that we ever reach in between from here to here, that's the answer. And here, the minimum is 1. That's precisely the connection. And so if we can answer these range minimum queries on our LCP array, we can compute the longest common prefix of any 2 suffixes, no matter where they are. They don't need to be adjacent. And that also directly solves the longest common extension problem, because they're the same thing. Okay? So provided that we have the suffix array, the inverse suffix array, the LCP array already computed, just solving RMQ on top of it solves longest common extensions. That's the final black box that we left open. But again, we shifted things only. We haven't solved the range min query problem. But I promise you we will. And it's again going to be building on only on things that you've already seen. As a little remark, the range minimum query problem is comparison based, so it doesn't necessarily care that the entries are numbers. It could be arbitrary objects that you can order. Also, like for the longest common extension problem, there's 2 running times plus the space usage. And it's to have a concise notation, let me write P and Q with these angle brackets for the pre-processing time and the query time. And any kind of solution will have some combination of these 2 times. Also note that if the pre-processing time is P of n, you don't have enough time to waste more space or fill more space with chunk than P of n. So the space you use is always bounded by P of n as well. We'll be content with that bound here, so we don't need a separate notation for that. in practice, that's a separate concern that you would also want to look at, saving more space. If you have any RMQ solution with such a quality, then we immediately obtain an LCE solution where you have the same running time, provided that the pre-processing is at least linear. The theta class doesn't even change. As always with new problems, you should first check what is the most trivial you can do. And the most extreme you can do is either do nothing at pre-processing time and scan the array at query time. That corresponds to constant time, pre-processing, or even 0, and linear time, worst case for queries. Fine, but not great. The other extreme is there's only n squared queries. Let's just pre-compute them all. If you do it stupidly, then it takes cubic time. If you do it slightly less stupidly, you can do it in quadratic time by reusing that you're finding the minimum of one range and then you make it one longer. No need to go from scratch and finding the minimum again. But still, you're paying quadratic time and space for getting constant query time. Maybe we can do a tad better. I think we'll actually have enough time to cover this. Is one more step we can go. The first non-trivial solution for the arrangement query problem is called the sparse table solution. And this is essentially very close to the pre-compute all possible answers, except that you try not to pre-compute most. You only keep a certain carefully chosen subset of the queries, chosen in a way that you can solve the others by puzzling together from the ones that you do save what the answer is. What do I mean by that? One specific way to do it is to only save, pre-compute the answer for queries where the length of the range is a power of 2. So we'll have this parameter L, the length of the range in the array that we look at, and assume that's 2 to the k. Then first of all, you can store those answers using k as an index instead of j. And also, more crucially, the number of things you pre-compute is only n log n, and all possible starting points. But then for each starting point, only the logarithmically many ranges of size is power of 2. Now that's fine. If your query has indeed a length power of 2, you're happy, you have the solution. But what if you do for all the others? Then you can't directly answer the query, but you can still figure out the answer in constant time. Namely, whatever the length of the query, doesn't matter. There's always going to be a power of 2 that's just below, but more than half. And so you find 2 overlapping or touching ranges. I guess they're always exact. They have to be overlapping. Otherwise, there would be one that covers the whole thing. But doesn't matter, actually. There's 2 ranges that together cover the query range. And so you'll get a minimum from the blue and from the green part. And certainly the minimum of the entire thing can be one of those 2 positions, but nothing else. Then you have to be a bit careful again with giving the leftmost priority and all that, but let's not be too strict about that. Essentially, the problem is solved. We find 2 positions from looking up the queries of powers of 2 size and comparing the values there in the array. And then we know in this case, 1 is smaller than 2. This is the answer for the query. So to write it shortly and ignore the type breaking, I guess, assuming argmin is doing the right type breaking, I just have to compare 2 values from the array. How good is this? I'm using n log n entries, so I have to compute those at the very least. But query time is constant. It turns out you can also compute every entry in this table in constant time if you do it in the right order. Namely, you go from small to long ranges. Then the next Next longer range consists exactly of 2 of half the size. So you do precisely the same trick as here to get the minimum of a new range that's double the previous 2. There's going to be 2 that cover it, and then there's the range min that you've computed iteratively before. You find the minimum of those 2, that's going to be the minimum of the entire range. So in constant time for each entry, you can compute this, which means the pre-processing time is n log n. That's the first solution that's somewhat usable. It still doesn't solve our original problem. We wanted linear time, but at least this is way better than the trivial solutions. And indeed, at this point, if you've seen enough of these examples, you may wonder if a simple trick is good enough to reduce from n log n to n by just applying this technique on a subsampled input. And that indeed works. It gives you a slightly different trade-off. If you take somehow a cleverly constructed input that has n divided log n elements, then n log n turns into linear time. Okay, that's easy. How can you use this here? One option is you break the array up into blocks of roughly log n numbers. Then you take the minimum of each of the blocks, and that's the array that you feed into the previous solution with the n log n pre-processing time, constant query time. So you can find if your queries are kind of rounded to block boundaries, you can solve the range min queries because you've found the smallest in each block. So any range that precisely covers an entire block will have to have as answer one of these blue positions. The only thing you can't immediately do is some range that doesn't align with block boundaries. But that's the last thing for today. If you have a general query, you can still do something. Namely, there's a part in the middle that has entire blocks, and that we already know how to solve. Yeah, and for the other ones, okay, that's bad, but at the very least, I could just scan them and find the minimum there, brute force. So if I do that, after I've found the minimum of the green guys, there's 3 possible values that I have to check. The overall minimum in the query could be this guy, or could be the best of these, or could be the best in here, and that's it. So far, we've covered how this works, and the intra-block queries I could do in logarithmic time, because that's the size of the blocks. So in total, what we've seen so far would be linear pre-processing time and logarithmic query time. That's again not what we wanted, but is another reasonable solution that's quite easy to get, and maybe a reasonable alternative to the things to come. But I'll leave it there, and how to get this down to constant we'll do next time.
You have the previous slide deck still open?
Yeah.
And you go to 49, slide number 49. No. No.
This one?